Okay, now we will focus on the second part, wireless LAN. So basically, wireless LAN, the standard for this is IEEE 802.11. It's a common wireless LAN that we see and we use in a day-to-day life. So, these are some basic requirements. Some of these you might realize is true in terms of free license. You're using an ISM band, maybe the band of operation 2.5 gigahertz, and of just like GSM or mobile phones that you're familiar with, need to move from one network to the other without cutting it off. Power consumptions, and a lot of other requirements in there. You can go through that. Different technologies are being used in the physical layer, basically infrared lens, wide spectrum lens, narrow band, microwave lens. If the question comes, this is the first thing that you should be trying, the IEEE 802.11 architecture. The overall box structure represents the extended service set. So within that, what you have is a basic service set. And what is coming under the basic service set is an access point and a station, station 2, station 3, station 4. This can be your devices, laptops or mobile phones, and your devices are connecting to the network via this particular access point. This is another access point and set of devices. And all these fellows are connecting, these access points are connected to the central distributed system. And this is connected via wired connection to the main network. The overall structure is the extended service set, which is nothing but a collection of various basic services. These slides just depict or gives more information to what we just mentioned. We can go through that. Access point is just like a wireless access point to which you are connecting. So there are two parts to this particular structure. The physical, we have already just mentioned briefly on what is the technology that is being used. And the second one is your data link layer. And in the data link layer, we are mainly focusing on the medium access control layer. And what does medium access layer gives you? It gives you reliability, access control, and security. Reliable because a lot of people are simultaneously using. You need to be given access to the person who wants to access at that particular point of time, and he has to ensure that no, your information is not being leaked to somebody else. So these three are the main requirements that is there. For reliable data delivery, that can be happening because of some loss. You can have some error checking codes, or you can have a higher layer structure in your TCP looking into that. In this particular structure, the most simplest one can be a frame exchange. Basically, the frame exchange is like you're sending a data and you're getting back an acknowledgement. If you're getting back an acknowledgement, this is meaning that the data is being received properly. So this is one of the most simplest way of doing it. And if you're not getting an acknowledgement within a span of time, you can go for retransmission. If you want to go one step further, basically in an 802.11, we'll be going with a 4-frame exchange. So basically there are 4 types of data that is being exchanged. One is request to send, that's a control signal. The second one is clears to send. And finally, you have a data and an acknowledgement that is coming. So these are the 4 frames. The first one says that I want something to send. And if the receiver says that I'm okay, I'm free now, he'll be reverting back with the clear to send. Now, once I get a clear to send, it's a signal for me to transmit. So I send my data. And once you receive the data, you'll send me back an acknowledgement. So these are the 4 methods of 4 frames by which you can ensure that there is reliability to an extent. And these are some alert signals for others also. We'll come to that later. Alert signals that somebody wants to transmit, or else this is another alert, can act as an alert along with a control signal saying that I am busy with something else, like this. If you want to dwell deeper into that, you say that you assume that your MAC layer is again divided into 2 sublayers. The first one is a distribution coordination function layer, and the next one would be the PCF. Now, this particular sublayer is for basically a conventional algorithm, and all the data and all the connections go through that. And if you want to have a little more priority-based, convention-based mechanisms, you have one more layer that is built on top of DCF. That is a point coordination function. And we can say that whatever comes through this is basically contention-free. And now, if you have a 14 marks question, this would be one of the important diagrams that needs to be drawn. You have the physical layer over here, and then on top of that, you have your MAC layer. And on top of that, you have your logical link control. Now your MAC layer, we said that it is divided into two. You have your point coordination function and you have a distributed function. So irrespective of what your technology is, all your data will be going through this particular sublayer. So that will be giving you some form of convention service. That is, if there is delays or whatever, you try to ensure that your data is being delivered. And no, if you have some higher priority stuff, what happens is that your data will be going to a point coordination function sublayer. And basically all the data coming through this or going through this would be contention free. So you can ensure that no, there'll be just imagine high priority data where you want to ensure that you have low latency, low delays, and all those things will be going through this point coordination function. So this is a generic org structure. So this is your physical layer. This much is your MAC layer, and this last is your logical link control. And we're talking about these two in your MAC layer. In terms of how much time should you wait for one transmission to be completed and the next to start, you have three names that comes over there, or durations that you can name. One is a SIFS. This IFS stands for inter frame space. Inter frame space. Or you can say it's a duration in this point. So SIFS is a short, from the name itself, it is the shortest. And basically it is used for control signals and like CTS, RTS, acknowledge and unknown. Now you have an intermediate duration structure that is called the PIFS. Then you have a longest one that is the DIFS, or distributed inter-frame space. And this is for that ensures that there is a minimum delay for all the asynchronous frames that comes over them. So we have the three timing duration structures. Now this is an algorithm. Sometimes this can be asked alone also. This is an algorithm to show how data transmission is done with a minimum set of reliability. There is always an improvement to this, but this is the most functional diagram. Now what happens? Now it starts from here. You have some data to transmit. So it goes and checks if the medium is idle. Now if the medium is idle, then what happens is that it waits for an IFS. Now at this particular point of time, we're not talking about whether it should be SIFS or PIFS or SIFS. So we're just saying that it is waiting for IFS duration. After that duration, if it is still idle, what happens is that you transmit that particular frame and you again check if you have anything else to transmit, and this particular moving goes on. So scenario one, we have no issues there and it transmits. Now scenario two is that you want something to transmit. At that time, the medium is not idle. That means somebody else is transmitting, so you have to wait for that transmission to be over. Once that is complete, now what happens is that you have to again wait for an IFS, and if it is still idle, you have an exponential backoff. This exponential backoff is just say that for each time you hold, you have to wait for, just say the first time you back off, you will be backing off for might be 0 durations. Second time you again have to back off, you might be wait for a little more longer duration. Third time you might need to again wait for a much longer duration. So likewise, that's why you call it an exponential backoff, because you are going to multiply your time. Basically, you're going to multiply your time with the factor k, how much times here. So if it is the first slot that you're going, the first lot will be basically from 0 and 1. So 0 and 1 should be multiplied by t, and you can choose random values from 0 and 1. If it is the second time, now you have to again wait. So it might be taking values from 0, 1, 2, and 3. So it can be either 1, 2, or 3, and that will be multiplied by t. Your t is your time duration, or that is dependent upon your bandwidth. So if it is a 1K system, it will be 1 by f. So if that is your frequency or band they're talking about, it will be 1 by f. That will be a t, and that you have to multiply with either 0, 1, 2, or 3. That depends on how long you're going to wait. Now, if it's the third time you're failing and you need to wait, it will be going with a much larger structure, 0 to 7. Likewise. So each time you go to this particular stage. That means the first time you want to transmit, you say that there's some problem there. You wait for that. You wait for IFS. If it is still idle, then you back up. Now, if it is not complete, you will go back here. Again, you wait for it to complete. Then you go for IFS, and if it is still idle, now the second time you come, it will be choosing from this set. Now, if it was not coming again here, it was going again through like this. What happens the third time it comes, it'll be choosing from the next set. So it goes on like this. So that is why you call it as an exponential backup. And once you finish up with your exponential backup, you transmit your frame and you go back to the social structure. So this is how you try to ensure that no, there is you are trying to limit the number of collisions that is there. Now, the next thing that you should be drawing in a 14 marks question might be what is the frame structure for an 802.1. Too much of elaboration might not be required. So you have a frame control. This is a place you just say that now we have one more structure here. This is a frame control structure. A lot of things coming over here. What's the most important thing is with the type. The type is basically can be an RTS, CTS, acknowledgement or data. RTS is a request to transmit, a request to send, clear to send, acknowledgement or data. So the frame control has a lot of things. In that we can say the type, duration. Then you have address 1, address 2, address 3, and address 4. Address 1 basically is a MAC address of the wireless host or access point to receive this particular frame. Address 2 basically is a MAC address of the wireless host or AP transmitting this particular frame. Who is transmitting it? This is basically the router address to which the access point is connected. And this is your particular data, and CRC is the error controlling mechanism that you have. So just to depict what that particular addresses are, you have this particular diagram over here. So you have a particular host that tries to transmit something. So this is the 802.1 frame that you're talking about. So this is address 1 that we're talking about, the access point address, then H1 MAC address. So this MAC address that is there, and the router, its MAC address will be address 3. Okay, so these are the 3 addresses that was there in your this particular structure and corresponding examples to that. And once it is going from the access point to the router, it is normally an 802.3 frame. Basically, it will be having a source address and a destination address. Destination address will be the router address. Source address would be the from where this is originating. That is your H1. MAC address would be the source address, and it is going to the internet. These are a lot of informations that you can go and have an additional reading to that. But if you have a 14 marks question, it's not necessary that you write all of these, but wherever possible, you can write. Now we talked about the MAC layer. Now about the physical layer a little bit. Now you can have, let's say, different standards associated to that. So different physical layer medium that can be there, direct sequence, FET spectrum, frequency hop, FET spectrum, infrared. That's like what we had seen in a few slides back. So you have the specification to that. Something that you guys are all familiar with or you might have seen is the type of 802.11 versions that you have that specifies what is the physical layer architecture that is there. You might have heard of 802.11 G/N. So likewise, you have different versions, 802.11 A, B, G, N, that specifies what is the spectrum that is using, what is the modulation that is being using, and what is the speed that is supporting. So the common wireless LAN that you see is majority of it would be saying that it supports 54 megabits per second. The latest 1 gigabits structures all will be supporting up to 200 megabits per second. So on that standard that follows is 802.11n. So these are some of the standards that is there or in terms of the technologies used for communicating. Now all these uses a version of multiple access scheme that is known as CSMA/CA. This stands for Carrier Sense Multiple Access with Collision Avoidance. Okay, one more, Carrier Sense Multiple Access with Collision Avoidance. Now we will be covering this in another video. Carrier Sense Multiple Access in short terms says that if I want to transmit something, I will sense the carrier and to check if somebody else is transmitting. If somebody else is transmitting, I just back up. And we have seen how you back up also. And /CA says that no, if there is a collision, You have to have a supporting protocol to avoid collisions, or if there was some collisions, what to do. So you have two standards over there, CD and CA. But what IEEE 802.11 follows is basically CSMA CA. Now, next thing goes with association. Association basically, now you turn on your Wi-Fi access in your mobile phones or laptops. What happens is that it will list out what are the available access points that is there, and they'll say, do you want to connect? And you connect, you click on it. Now, if it's the first time, that means you're not associated. You have to associate. They'll be there. If it is a password protected, they'll be asking you for your passwords, and type in your passwords, and then what they have is you have your DHCP and all those things running to give you a free IP address dynamically, and then you are connected, and then you are able to use it. And you see, if you set it to automatic, next time you come to that particular space and your Wi-Fi is on, it'll automatically connect. Or else, if you don't set it automatically, each time you have to connect. But still, you're already associated. And the name that comes over there, the information to that, or the naming that you give to is SSID. Okay. Now, what are the two what is it, protocols that is there so that you're able to connect? Now you have something that is known as passive scanning and active scanning. Now, passive scanning basically it is the access point that always sends beacon signals. Always, it sends beacon signal saying that yeah, I am here, I am here. Likewise, that is what you see over here. Access 1 is sending a beacon. Access 2 is also sending a beacon. Now, this host can choose which one should it connect to. So it chooses, say, this access point 2 in this particular example. So it sends a request for association. And if it is OK and everything is fine, it will confirm and H1 is connected to access point 2. Now, if it in active scanning, what it does is that H1 says that, no, is there anybody here? Is there anybody here? It sends a request probe like this. That is what you see over here. Now, once access 1 and 2 receives that particular request, they send back their response. Yeah, I am here, I am here. So these two access points lists are there. And H1 then chooses its appropriate access point. Here you see that it chooses AP2 and it sends a request and it sends back the response to that. And H1 is connected to access point 2. So you have your two versions of scanning and you are connecting. So you have association to a particular access point, and finally, if you don't want to again log into that, you can deassociate, delete. Another important point that comes over in 802.11 is the multiple access scheme. I think we have already discussed this in a previous session in terms of the hidden node problem. So this is an example for a hidden node problem. A is hidden to C because its strength is almost 0, as well as C is hidden to A because its strength is almost hidden 0 over here. But they both are visible for B because their strengths are almost strong enough. So just like what we have mentioned before, if they sense the channel, okay, that is the first thing that they do. So A senses a channel if somebody is there. So they both are trying to transmit similarly. So at this particular point of time, nobody senses, A doesn't sense the presence of C, so it transmits. Likewise, C doesn't sense the presence of A, so it transmits. They both transmit, and at a particular point of time, what you see over here is that they both collide and the data is lost. So irrespective of, say, that you have a carrier sense multiple access protocol, you see that both these data are collided and it will be lost. So you need to have not just CSMA, that is carrier sense multiple access is what we have done. What you need to have is collision avoidance mechanisms also. So we already talked about collision avoidance in a particular form, but we'll just see what that particular thing is. So this is the most simplest form. So sender A has something to send, so it waits for some duration. So this is what we set up your interrupt frame space. So it waits for a certain duration, that is DAFS, sends the data. And once it gets the data, it waits for an SIFS duration and then sends back an acknowledgement. So these point of time, what they're doing is they're waiting if the channel is free and all those things. So you have a waiting duration so that you can avoid collision. So this is the most simplest of it. But this doesn't solve the whole thing because this is the case, we'll see that the second figure is more explanatory. So there can be collisions here still. So what we do is that we go one step further. We can have the four-frame structures, RTS and CTS. We'll see how that particular thing is. So just say that you have two nodes A and B and your access point in between. They both want to connect to your access point, or they both want to send some information to the access point. So what do they do in four-frame format? A sends an RTS to access point. Likewise, B also sends an RTS to an access point. So what happens is that at this particular point, even because of the hidden node problem, and this green shade, what you see is here it is dark and here is getting light, and no green shades coming over here. That means its energy is diminishing. But still, what you see is that they both data get collided over there. So what happens? They wait for some random duration of time, backup. And after some duration, what happens is that your A transmits a request to send. Access point sees it, and since it doesn't get anything and gets all those things, what it does is that it sends the clear to send signal. So what you see, based on this, access point sends a clear to send to A. But the transmission is not just one direction, it goes bi-direction, because you cannot constrain your transmission to one direction. So once the access point sends it to A, it is also seen by B. So that means what? Once that clear to send is received over here, A transmits the data. But since B has received this particular signal, that is CTS A, it knows that no, A access point is doing something else. So it has to stay back. So that is why you say that it is differing. It's staying back. And what you see is that A transmits, the access point gets it. And once everything is done, what does the access point do? It sends an acknowledgement. You see that acknowledgement is sent to A. Likewise, since it is transmitting on to A, even B also sees it because the energy is seen on both sides, right? So B also sees it. So once the acknowledgement of A is received, B knows that, yeah, now your A access point is free. Now I can transmit. So what will be the next thing? Next thing would be after some duration of time, B sends RTS of B. If there is no collision, what happens is that your access point will be sending CTS of B. And once that is received, what B does it sends a data B. And then what your access point, once it gets it data, it sends an acknowledgement B. For acknowledgement B to B as well as to A. At that time, if A again wants to send something, it can transmit. So this is carrier sense. What you see is the first line is basically carrier sense. It's sensing if somebody is transmitting or not. So they both could not, since they could not see, they both transmitted and collision occurred. Now what happens? You have your collision avoiding mechanism. So this is the collision avoiding mechanism that comes over here.